4.24 on page 197. To start, I am going to reference example 3.8 on page 145 through 147 of the text. This was the problem of a conducting sphere placed in an otherwise uniform electric field. I am going to refer to some of the results of that problem and not explain them, so if you do not remember that, please brush up. So for this problem, we have a conducting sphere surrounded by a dielectric shell inside or in free space. If the sphere and shell were not there, there would just be a constant electric field. I am going to refer to the properties of the three regions using subscripts F, D, and C. F for free space, D for the dielectric shell, C for the conducting sphere. If you recall, one of the results of the example problem 3.8 was that the only Legendre polynomial term that mattered was the L equals 1 term, which means that we can say the potential inside any of those regions is given by the formula V is equal to AR plus B over R squared times cosine of theta. This gives us 6 unknown terms. The A and B terms of the free space, A and B of the dielectric, and A and B of the conductor. Now 3 of them we know right off the bat. Because of the similarity to example 3.8, we know that in the free space, the A term is equal to E naught. That is the strength of the electric field where there's no sphere. We also know that inside the conductor, potential is constant, which means AC and BC are equal to 0. Our next conditions come from the fact that potential should not experience any discontinuous jumps, which means A times R plus B over R squared should be the same in the boundary regions. So calculating for free space and calculating for dielectric, they should be the same when R is equal to B, and dielectric and conductor, they should be equal to each other when R is equal to A. That gives us these two conditions. This is for the boundary between the dielectric and the conductor. This is for the boundary between the dielectric and the free space. One more equation, on equation 4.41 on page 192, which in the main lecture I use this. The change in this quantity epsilon dVdn depends on the surface free charge density. However, in the boundary between the dielectric and free space, there is no free charge. All of the surface charge is bound charge, which means this is 0, and so this quantity epsilon dVdn should be the same both outside and inside the dielectric. Now, because we're dealing with spheres, the n is the radial component, so n is r. So we can calculate dV/dr from this formula right here. A times r becomes a, b over r squared becomes negative 2b over r cubed, and cosine theta is unaffected. So the dV/dr for free space should equal dV/dr times epsilon r for the dielectric. Both terms have a cosine theta, so I have ignored it, written this equation. So with these 3 equations and these 3 known quantities, we can say first equation, second equation, and first equation, this comes from the boundary between the dielectric and the conducting center. This one comes from the boundary between the dielectric and the free space. Notice the epsilon naught is replacing AF. And this equation comes from our equation 4.41. I have again placed epsilon naught into AF. What comes next is algebra. So first, I took equation 1 and I solved for AD. That gives AD is equal to negative BD over A cubed. Next, I plug that value of AD into equation number 2, and I solve this equation for BF. And I got BF is equal to BD minus BD times B cubed over A cubed, which was this, with this replacement, minus E naught B cubed. Next, with this AD in terms of BD, and with this BF in terms of BD, I plugged both of these into our third equation, and I got this. So epsilon, or E naught, 2 times BF over B cubed, BF is this, so 2 times BD over B cubed, plus, because minus, plus 2 times BD times B cubed over A cubed divided by B cubed, or plus 2BD over A cubed, plus 2 E naught B cubed over B cubed, so plus 2 E naught, equals negative epsilon R BD over A cubed minus epsilon R, minus 2 epsilon R BD over B cubed. That is quite a mouthful. So E naught and 2 E naught, I combine them to 3 E naught, and all the terms linear with BD I move to the right-hand side. So 2BD over B cubed became BD times 2 over B cubed. Negative, or 2BD over A cubed, move that to the other side, became negative 2 over A cubed. Negative epsilon R BD over A cubed minus epsilon R over A cubed, minus 2 epsilon R BD over B cubed, minus 2 epsilon R over B cubed. So we can solve for BD, and with a couple clever arrangements, BD is equal to this term right here. Since I already had AD in terms of BD right here, I did that. Now I could have simplified a little bit more, but I'm leaving it like this. Now one thing I would like to point out is that even though AD has this explicit negative and BD does not have an explicit negative, the relative permittivity is always going to be greater than 1, which means that this term is negative and this term will also be negative. So BD will have a negative quantity no matter what numbers you plug in, as will AD. And AD will be positive no matter what numbers you plug in. Now that would be enough for us to find the potential inside the dielectric, but the problem asked what is the electric field inside the dielectric. So to find the electric field, we say the electric field is the negative gradient of potential. Using the gradient equation for spherical coordinates, the R component of electric field is given by this term right here. Notice I'm leaving it in terms of AD and BD. So AD and BD. And the theta component of electric field is given by this formula right here.